Hello and good afternoon. My name is Francesc Fàbregas. I work for DNVGL Bristol, and in this short presentation I'm going to outline some research challenges that are relevant for floating wind from an industry perspective. So the first challenge that I wanted to mention is rather specific, but I thought it would be of interest as it's something that we've had to deal with recently in the context of a floating wind project that I've been involved with, and it's related to wave stretching. So in industry, we often use linear random wave theory. So this means a linear superposition of regular waves to describe a random sea state. And in doing so, we assume that all these waves are free, but we know in reality some of them are bound. So this means that some waves are riding on top of other waves. And the consequence of this is that when we try to derive wave kinematics, velocities and accelerations, especially close to the water surface, if we use this linear random wave theory, we can significantly overpredict these velocities and accelerations. And then if we use this in Morrison's equation, for example, to predict loads, then we can similarly overpredict the loads. So to avoid having this problem, stretched waves solutions have been proposed. So even if we know that these stretched solutions are not physically correct, they're quite often used in industry, I think, because they are quite straightforward. And I've included here in the slide some references to standards that refer to some of these available stretching techniques. And one of the most widely used in industry is what we call Wheeler stretching. So the challenge that we had in this recent project is that we used two different stretching techniques, and we obtained two very different results, in this case regarding tension in the mooring lines of the floating platform. So this is what's shown in this figure, which shows two time series of mooring line tension. One is calculated with one stretching technique, the other one with a different one, and you can see that the differences between the tensions predicted in the two cases are quite significant. So I think it would be useful to compare stretching methods or different stretching methods against more accurate solutions for representative floating wind platform designs and also environmental conditions to better understand the implications of using one or another, and also to have a quantitative measure of how wrong we might be. So the next challenge that I wanted to mention is the modeling of hydroelasticity in floating wind platforms. And in this case, this is in view of the floating wind systems of the future, which will feature very large wind turbines, probably of 15 megawatts or more, and this very big turbines will be mounted on optimized floating platforms, and by that I mean platforms with as little structural mass as possible. So this means that the structure will deform, and this is shown schematically in the figure in the slide, and this will affect the hydrodynamic loads and vice versa. So we see that hydrodynamic loads and deflections are coupled, and this is what we understand by hydroelasticity. So to model this numerically, mainly we need a structural model that is coupled to distributed hydrodynamic loads instead of integrated loads, and this is what's typically done when the whole structure is considered rigid. So in this slide, I've written down some examples, and by no means it's not an exhaustive list, but these are some previous studies that have looked at calculating distributed loads in different types of floating wind foundations, and you'll see that most of them only consider linear effects. So the challenge is then in incorporating higher order loads, for instance. So I've tried to summarize in this table some of the methods that have been proposed in the literature. Some of them have been widely used, like Morrison's equation, but others are more recent, like the fluid impulse theory, the FIT. And so from an industry point of view, it would be useful to see how these these new approaches can be implemented consistently, and then to have quantitative comparisons between them. So if we stay in the context of engineering models, Morrison's equation is commonly used in early design stages to calculate hydrodynamic loads on floating wind platforms. And this equation relies on drag and inertia coefficients, which in turn depend strongly on several flow parameters. So the Casey number, the Reynolds number, and probably also on surface roughness as well. So the challenge here is that we have drag and inertia coefficients for heave plates that come from the oil and gas literature, but so these coefficients might not be suitable for floating wind applications because the heave plates in this case might not have the same dimensions. The amplitudes of motion of the floating wind system will typically be larger than in an oil and gas application, and also this heave plate, for example, will be closer as well to the free surface, so they might interact with the free surface as well. So I think it's a topic that deserves more attention, especially because the effect of these coefficients on the global response of the system and also the loads can be quite significant. And so finally the last challenge that I wanted to mention is probably more of a broader theme, which is related to the use of high fidelity tools. So until now I've mostly talked about engineering tools, which might not be appropriate to predict loads and the response of the system in extreme environmental conditions, so extreme waves, winds and currents superimposed. And in this case, it's typically breaking waves and wave slamming become important. So these effects can be handled by more sophisticated numerical modeling techniques, for instance, CFD or SPH, that can be, for example, coupled with other models, a structural model, a mooring model, or even the model of the wind turbine. So in this context, I think the challenge from an industry point of view is how to make these models that are typically developed within research institution available to companies, or to make them as easy as possible to run, and also to develop best practice guidelines tailored to this specific field, so floating wind applications. And I think another very important thing to tackle is the efficiency of this method. So reducing computational time is very important. And so related to this then, an important question as well is how to select the load cases that should be run in these computationally demanding codes. And I think this is especially relevant for floating wind, where the number of possible combinations of wind, waves, currents is quite large. And finally, I'd like to note this recommended practice from DNVGL that was published recently on the couple analysis of floating wind turbines, because I think it's a good point to start that provides the industry point of view of the state of the art and the questions that are still open in this field. So thanks very much for your attention, and please let me know if you have any questions.